Hi, my name is Matthew Yakov, and in this video we're going to talk about the most common use cases for the SD-WAN deployments behind NAT. Let's review the most common implementations of the branches behind NAT. So let's imagine that the devices at the bottom, or the users at the bottom, those are the SD-WAN devices which can be behind the NAT to access internet servers or internet resources. So the two most common use cases in this case is the static NAT, which is very commonly used in the AWS or in Azure or any other cloud deployments. Or the second type is the port address translation or network address port translation in Juniper terminology, where multiple devices or multiple users are behind the same public IP, behind the same NAT, trying to access internet resources. Now, let's review in details what can be done in each of these use cases. So let's say that we have a user or SD-WAN device which is behind the static NAT. In this case, when this user has IP address 10.0.0.1 and it tries to access something with the IP 2.2.2.2, and at the same time he is translated using static NAT to the IP address 1.1.1.1, the operations will happen in the following way. So first of all, the initial packet is going to be originated from the IP address of this device or user from 10.0.0.1 to the IP address 2.2.2.2. We will have certain source port and certain destination port. So in this case, we're trying to access port 22 to access SSH connection. When the packet will reach the NAT device, it will be translated into the 1111 to the 2222 with the same source port and the same destination port. So you can check that source and destination ports, which were 24, 680, and 22, they didn't change when we switched the translation on the static NAT. Next, example number 2, the same topology where we have static NAT, but in this case the connection is being originated from the outside, from the external location, from the server on the internet, which is trying to reach our SD-WAN branch or our user on the left. In this case, traffic will come to the static NAT, will be translated again with the same ports, and will traverse back. So the static NAT has a specifics that the translation always happens in both directions, no matter from where the traffic is originated. So once again, the translation will always happen both ways, no matter who initiated the session, the device from the left side of the static NAT or from the right side of the static NAT. It will always be successfully translated between the two devices. Now let's review the port address translation or network address port translation use case with the TCP connection. So in this case, we have multiple devices in the local network behind the network address port translation device. We have external IPs 1111 and 2222. And in this case, the user with IP address 10.0.0.1 is trying to open SSH connection to the server 2222. In this case, the packet will reach the network address port translation device, and on the NAT, the system will create the translation table in which it will have the IP address of the internal user 10.0.0.1 with the original port with which the connection was opened, then external IP address to which we're translating it. And look at this, with the TCP connection, it uses the different external port from the original one which we initially originated the connection with. The external port and IP address are not changed. So after that, the connection just goes to the right side and reaches the server, and it's being established. Now, at the same time, if the second device from the local network will also try to establish connection to the outside world, to the external server. So in this case, from 10.0.0.2 to the 2.2.2.2, the destination port 22. But the source port might be slightly different. When this packet will reach, again the translation will happen, and again we will find the new source port newly generated on the NAT device, which the system will originate the connection from. So look at this, both source IP and source port were changed. This is the way how the TCP translation on the regular network address port translation device works. Now let's review how the return traffic works. how does the NAT device knows to which device on the internal network with the TCP connection to send the traffic? So let's imagine that we receive the connection from the device 222 to the IP address 1111, and in this case from the source port 22 to the port 29871. In this case, system knows that this should be translated to the 10002 device because of the source port from which the connection was originated on the network address port translation device. So it will know where to send it properly. Similarly, if there is going to be anything coming to the port 46862, it will translate it to the first device because, once again, according to the translation table, this NAT device will know how to properly use it. Now let's go and review how it works for the UDP, because for UDP it works slightly different. And once again, in here I'm explaining how it works with the RFC compliant devices. So we're not talking about the third-party use cases for somebody who's not doing it according to the standards, industry standards. In this case, I'm describing how it's done in Cisco, Juniper by default in most of the use cases. So for the UDP traffic, when, let's say, the device 10001 establishes SIP connection over the port 5060 to the destination device, and this connection goes through the network address port translation, again, the system will create the translation table, but in this case, the source port will be kept the same. This is just the way how it operates by default for UDP traffic, and it will be sent out. But now you can ask me, what if another device from the internal network will also try to establish connection to the external device? What will happen in this case? So this I purposely even checked the RFC, and it was said that the UDP port which will be assigned on the external connection will be the same plus one. So in this case, 5061 will establish connection to the 5060 on the external device. The same will work for the majority of the computer games and other UDP using applications. So again, the same way, it will always translate this way. Now, let's review another use case. This use case, again, according to the RFC, but what if this NAT device actually has some service which is listening on the port 1111 on the port 5060? How the translation will happen in this case? In this case, if the internal device will try to establish some connection, the translation table will work exactly as for the TCP traffic. It will just choose the random source port to do the translation. And once again, this is only in cases when there is already something listening as a service on the NAT device. So the translation is going to happen very similar to the way how it's going to be in case of TCP traffic. Now, let's review one more use case, so-called endpoint independent mapping. So this is one of the operations which can be configured on the NAT, and in certain cases it's actually extensively used. I'm going to show you later which use cases in Verse utilize this specific connection. So let's imagine that the device 10001 is opening connection to the 2222 from the source port 4790 to the port 4790. That's actually how our devices establish SD-WAN connection to the other locations. In this case, when the packet reaches network address port translation device on which we have configured network address port translation with endpoint independent mapping, the translation will happen that from the 10001 port 4790 to the external source 1111 on the network address translation device with some port, but we will have in the network address translation table that the destination can be anything. Doesn't matter from which device it's coming to the port 15 to 379, it will always be translated back. What this means? This means that when the packet will come back from the device 2222, it will be translated properly to the device 10001. But also, if the device to which the device 10001 never communicated to, in this case device with the IP address 3333, will try to establish connection to the same port on this device, it will still be translated properly to be translated inside. So this is very important to understand because this mechanism can be configured separately. In certain cases, it's used by default in some of the vendors. Majority of them don't use endpoint independent mapping, and it will work like we had examples with UDP and TCP previously. But in certain cases, it's possible to enable endpoint independent mapping. Let's see where it is used in Versa construct. In Versa construct, on the right, we have branch 2 device, which has two VRFs, one for the internet, second for the MPLS, and it also has the control VR, where we have the SD-WAN engine running, and we have the LAN VRF. Similarly, on the left side. So here we have the cross connect, which is used by the branch 1A to access MPLS network. So in this cross connect, we will always have the same IP addresses, 172.16.255.1 on the first device and 172.16.255.2 on the secondary device in here. So what will happen and how the translation will work? When the device branch 1A first connects to the controller, it will inform it. So, hi, I'm branch 1A. My LAN networks are this. And if anyone wants to reach me, my WAN IP addresses, internet is reachable via 1234 port 4790, and my MPLS is reachable via 172.16.255.1 port 4790. And most importantly, he will inform that his paired site ID is, for example, site 1. Now look at this. Because the IP address 172.16.255.1 is the local address and it's never reachable through the internet, technically nobody should be able to reach this device by this IP address. But the trick that we are using at Versa is that whenever the device branch 1A will send out any packet from the source port 4790, so let's say it's sending it out, at that exact moment, we will do the translation with endpoint independent mapping. For example, in this case, 172.16.255.1, which is branch 1A, with the source port 4790, was translated to the external IP on the MPLS VRF of the branch 1B. And in this case, let's say that we just give the source port 10,000. And the translation will be endpoint independent mapping. At this exact moment, the branch 1B will say, hey controller, my paired site ID is the same as the other guy. I don't know what's that guy IPs or what's happening on that guy, but somebody with the same paired site ID just tried to send packet through my MPLS WAN, and I did the permanent translation with endpoint independent mapping from the 172.16.255.1 to 5678 port 10,000. If anyone wants to reach my paired site through me, he can reach it using the IP address 5678 port 10,000. So this way, if branch 2 would like to initiate connection to the branch 1A via MPLS, he can just reach out to the IP address 5678 port 10,000. But at the same time, if branch 2 would like to establish connection with the branch 1B, he can just establish connection to the 5678 port 4790, which is going to be configured on this MPLS VRF. Okay, now let's review a couple of use examples for the SD-WAN branches behind NAT. So let's imagine that we have Versa OS device deployed somewhere in AWS. Internal IP address in this example is 10.0.0.1. We have some external IP address 1.1.1.1, and we have external IP 2.2.2.2. The connection is pretty simple. So branch A in this case will inform the controller that if anyone wants to reach me, my internet connection has the IP address 10.0.0.1.4790. I mean, of course, this is not something which will be reachable through the internet, but look at the trick, what is happening. The controller, when he received the message from the branch A, will also mention that the actual connection from the branch A came from the IP address 1.1.1.1 port 4790. And the interesting thing that the controller will inform everybody else that the branch A has WAN network 10.0.0.1 with the port 4790, but also there is a chance that alternatively you can reach the same WAN interface of the branch A through the IP address 1.1.1.1.4790. the controller doesn't know which way the branch B would be able to establish connection to the branch A. So he will send just all the possible information to the branch B. And in this case, of course, the connection will be established because the branch B will see that he has two possible ways to connect to the branch A. He will try first, for example, to the IP address 10.0.0.1, which was informed first. He will send it, and the packet will successfully die somewhere on the internet because it's unroutable through the RFC 1980 over the internet. Then it will try another establishment of the connection, and it will try to establish it from the IP address, from its local IP address to the IP address secondary, which was reported by the controller, in this case 1111 port 4790. And of course connection will happen and will be properly translated to the device, and the two branches, branch A and branch B, will be able to establish connection. Next, let's review example, but in this example, instead of static NAT, we will have network address port translation. With the standard translation, let's say that it's a default deployment somewhere on Cisco device or Juniper device or on Versa device, which is doing NAT. In this case, once again, those are the IPs that we have. When the branch A will try to inform the controller that he has the IP address 10.0.0.1 port 4790, and this connection will go through the network address port translation device to the controller on the NAT device, there will be established the session record that from the IP address 10.0.0.1 port 4790 to the IP address 4444 port 4790, we should translate it to the external IP 1111 and external source ports, let's say 12345. But this also means that the branch B would not be able to establish connection here because this translation is only happening between IP address 10.0.0.1 and IP address 4444. So in this case, once again, the controller will see that, the IP address which was reported by the branch A is 10.0.0.1 but I received connection from the 1111 port 12345. I will report both of these IPs to the device branch B. When the device branch B will try to establish connection to any of these IPs, let's say to the 10.0.0.1, it will be lost on the internet. If, in this case, the device will try to establish connection to the IP address 1111 port 12345, the packet, of course, will reach the network address port translation device, but there is no record which indicates the connection between 10.0.0.1 and IP address 2222. So the NAT device will just drop this packet. It doesn't know how to do this translation. So in this case, we have a question. How is it possible to establish connection between these two devices? The interesting thing that branch B will also inform the controller about its connections and about the way how it is possible to establish connection in there. So when the device branch A will try to establish connection to the branch B, we will create a second record on the network address port translation device. The second record between 10.0.0.1 and 2222. The source port after the NAT device will be different. And in this case, the connection will be reached and they will be able to establish connection because the reply packet from the branch B will know how to be translated by this network address port translation device. Okay, and now let's review another example number 2. In this case, let's say that both of the devices, branch A and branch B, are located in the same location behind the same network address port translation device. When the branch A will try to connect to the controller, he will inform his local IP address and controller will see the external IP from which the connection came. He will report it to the branch B. Therefore, when branch B will try to establish connection, he will try to do it in two ways. First, maybe it will try to connect to the 1111 or maybe it will try to connect to the internal IP address. If the NAT device allows to do translation from the internal network to the external IP and back, then it can be translated. But many devices would consider it security violation and not allow this. So the second attempt from the branch B to establish connection will be just to the internal IP address. And the connection will be successfully established. So this way we will be able to properly establish connection even for two devices which are behind the same network address port translation. Now let's review another example. What if we have multiple SD-WAN branches behind NAT? If we have network address port translation on one side and static NAT on the other side, the connection without any problems will be able to be established. So we'll just establish connection from the branch A to the branch B. Only this packet will be able to traverse from the network address port translation device, properly be translated, and then go through the internet to the device, translate it again. Because it's a static translation, it will reach the branch B. And we successfully establish connection. While at the same time, if we have multiple devices behind different network address port translation devices, they will never be able to establish connection to each other. The only solution that we have in here is to deploy hub device through which those devices will be connected. So in this case, if branch A would like to communicate with the branch B, branch A will establish connection with the hub, branch B will establish connection with the hub, and the packets will go from branch A to hub and from hub to the branch B. But the mandatory requirement is that hub must have external IP address. It should be either behind static NAT or it should have the real IP address on its external interface. I hope this was informative for you, and thank you for watching.